Now that we understand the addition rule and the multiplication rule, and we've started to talk about conditional probability, we want to talk about Bayes' theorem, which is a really important concept in probability. And just walking through the theorem itself is a little confusing, but when we use an example, it's actually not too tough. So the theorem itself says the probability of event A happening, given that event B has already occurred, is equal to the probability of B given A multiplied by the probability of A divided by the probability of B. And remember, with all these probability formulas, we can let event A and event B be anything we want to. We're just using A and B as placeholders. So as an example, so that we can understand what this theorem is actually doing, let's say that we have two factories or assembly lines. So we have assembly line 1 and assembly line 2. And let's say that 3% of the parts produced on line 1 are defective, while 1% of the parts produced on line 2 are defective. In other words, we've been studying these assembly lines over a long period of time. We've taken lots of samples, and we already know that the defective rate for line 1 is 3%, the defective rate for line 2 is 1%. That's kind of historical information that we have. Okay, so we have defective rates for each of these lines. What Bayes' theorem allows us to do is answer a question like this one. So given that we got a defective part, what is the probability that it came from line 1? Or we could say came from line 2. In other words, we're getting defective parts from line 1, we're getting defective parts from line 2, but we're getting them at different rates. Now we have a defective part in our hand, and we want to know the probability that it came from one line or the other. It's almost like calculating the probability of something in the past or going back in time. I have a defective part at this point. I don't know which assembly line it came from. I want to know the likelihood that it came from line 1 versus line 2. What's the probability that the defective part came from one assembly line versus the other? So to use Bayes' theorem to answer a question like this one, the first thing we always need to do is identify event A and event B, right? Our Bayes' theorem formula is given to us in terms of events A and B. We need to now assign those things real names so that we don't get confused. So this is saying, given a defective part, what is the probability that it came from line 1? And Bayes' theorem allows us to calculate the probability of A given B. So if we match up that language to the question that we're trying to answer, the probability of event A given event B, given that event B has already occurred. Well, in our question, we're saying, given that we have a defective part. So we're going to say that event B is the event that we get a defective part. So given that we pull a defective part, what is the probability that it came from line 1? What is the probability of A? A must be coming from line 1. So we're saying event A is the part coming from line 1. Event B is the part being defective. Now we need to calculate these three probabilities on the right-hand side of the theorem. So let's start with the probability of event A. So the probability of event A is the probability of the part coming from line 1. Well, let's just say that there's an equal likelihood that we choose a part from line 1 or line 2. So we'll say that this probability is 1/2. Now, this could change. For instance, if line 1 produces 90% of all of the parts and line 2 produces only 10% of all of the parts, then the probability that the part comes from line 1 would be 90% or 9/10. But if we say that 50% of all the parts come from line 1 and 50% come from line 2, then there's an equivalent chance of choosing line 1 or line 2, which means the probability of event A choosing line 1 is 1 out of 2, 1 and 2, 1/2, 50%. Now, the probability of event B, given that A has already happened, is simple as well. In fact, we've already been given it in the information in the question. This probability is the probability of a defective part, event B, given that the part comes from line 1, event A. Well, we already know that that probability is 3% or 3/100, because if the part is coming from line 1, we know that line 1 has a 3% defective rate. So the probability of the part is defective, given that it comes from line 1, is 3/100. So these things are easy to calculate. The toughest probability to figure out is the probability of event B, the probability that the part is defective, because we have to consider both line 1 and line 2. Let's first think about the probability that the part comes from line 1 and is also defective. Well, remember our multiplication rule. If we say the probability that the part comes from line 1 and is defective, or we could write this as line 1 and defective, is equal to, this is our multiplication rule. We have to multiply the probability that the part comes from line 1, which we know is 1/2, by the probability that the part is defective, which we know is 3/100. So 3/100 or 3/200. Now, the probability that the part comes from line 2 and is defective, again, is our multiplication rule for independent events. We get the probability that the part comes from line 2 multiplied by the probability that it's defective. For line 2, that's 1/100. So we're going to get 1/200, which means then that the probability of a defective part we get using the addition rule. It's the probability that the part came from line 1 and was defective, or came from line 2 and was defective, because either of those scenarios would result in a defective part. And so we have to then add these two probabilities together. So 3/200 plus 1/200 is 4/200 or 1/50. So the probability that the part is defective is 1/50. Now, with all three of these values, we can actually calculate the probability we're looking for using Bayes' theorem. So let's actually write this all out. We'll say the probability that the part came from line 1, given that it was defective, is equal to the probability that it was defective, given that it came from line 1, 3/100, multiplied by the probability of event A, the probability that it came from line 1, 1/2, all divided by probability of event B, the probability that it was defective, which in this case is 1/50. And when we do that math, we get in the numerator here, 3 times 1 is 3, 100 times 2 is 200. So we get 3/200 divided by 1/50. When we divide by a fraction, that's the same as multiplying by the reciprocal. So we say 3/200. And then instead of dividing by 1/50, we multiply by 50/1. We flip that fraction upside down, and we get 150/200, which simplifies to 3/4, or 75%. So there's a 3 in 4 chance, or a 75% chance, that the part came from assembly line number 1, given that the part was defective. So if we're holding a defective part in our hand, and we don't know whether it came from line 1 or came from line 2, we know that the probability tells us that there's a 75% chance, there's a 3 out of 4 chance that the defective part came from line 1 compared to line 2. And of course, given what we know about complementary probability, if there's a 75% chance the defective part came from line 1, that means by definition that there's a 25% chance that the defective part came from line 2. Now, there is another tool we can use to answer questions using Bayes' theorem, and it's this idea of a tree diagram. And this is something that helps a lot of people because this formula itself can be confusing. It takes some practice. Sometimes it helps to see a visual. So the idea here with this same question is that we have an equally likely chance of choosing line 1 or line 2 because these assembly lines each produce 50% of all of our parts. So we have a 50% chance of choosing line 1 and a 50% chance of choosing line 2. We could also write this as 1/2 and 1/2. And so we build out this first decision in our tree diagram. And then from here, off of assembly line 1, we can get defective parts, or we can get what we'll call compliant parts or non-defective parts. Well, we know that line 1 produces defective parts at a 3% rate. So we could say that this is 3% or 3 in 100, which means compliant parts are produced at a 97% rate or 97 in 100. And then off of assembly line 2, we can get defective parts. Line 2 produces defective parts at a 1% rate. So we can say 1% here or 1 in 100, which means that line 2 produces compliant parts at a 99% rate or 99 in 100. Now, going back to our same question, given that we have a defective part, what is the probability that it came from line 1? Once we've built out this tree diagram, this decision tree, what we want to do is sort of trim off all the branches or ignore all of the paths in the tree that don't lead to the question we're trying to answer. In other words, we're looking at defective parts only, not compliant parts. So we can sort of ignore this whole part, we'll cancel out that part of the tree, cancel out this part of the tree. We're ignoring all of the compliant sides of our tree and just looking at the defective sides. So what we can say then is that the probability that we chose a part from line 1, given that the part was defective, so we'll say the probability of choosing a part from line 1 is going to be equal to, we look then at the number of branches that lead to defective from line 1, this number right here, so 3, and we divide that by the total number of branches that lead to defective anywhere in our tree, which is this value 3, but also this value of 1. We have 1 branch leading to defective here, 3 branches leading to defective here, and so we say 3 plus 1, or 3 over 4, which is that same 3 out of 4 number we calculated earlier, that same 75% figure, as the chance that our part came from line 1, given that it was defective. We could obviously use this same tree diagram to see the probability that the part came from line 2, given that it was defective. So we could say the probability that it came from line 2 is equal to, we would take this value 1, divide it by the total possibilities, 3 and 1, so 3 and 1, and we would get 1 over 4, or 25%, which of course we already know to be the case, because 100% minus 75% gives us that 25%. These are complementary probabilities. So that's the fundamental idea behind Bayes' theorem. Given that I'm holding a defective part in my hand, and I know that assembly line number 1 produces defective parts, and assembly line number 2 produces defective parts, what's the probability, what's the likelihood that the defective part I'm holding was built on assembly line number 1 or was built on assembly line number 2? It's kind of a way for us to look back in time to figure out the likelihood that some event occurred in the past, given the fact that we know that the part we have is defective.